So I will try to tell you a fairy tale about security. The first thing I need is a damsel, in this case, in distress. And what is in distress here are secrets that are stored in all of your electronic devices. And I don't want to spend too much time on that because you will know what computers you carry around and what sort of secrets they have on them. This one is even worse here because my entire life on them, including payment options. And these things need to be, right? And what are we up against? We need a dragon as well. And the dragon of the day is side channel attacks. And you all know about side channel attacks because you watch movies. So a side channel is an unintended communication channel that the device has. In this case, we have a safe box, and what you're supposed to do is turn the dial. If you turn it to the right order, the right length, multiple times, then you can check the handle on the safe box, and you will see if the combination was correct or not. And what this gentleman here is doing, obviously, is listening to the noises that emanate from the lock, and he's drawing conclusions from that and making his path to attack shorter. And you have the same principle that you can use to attack electronics. Now there is side channels up to wazoo. Today we're going to talk about power side channels and electromagnetic emanation. And for all intents and purposes for today, they are the same thing. So the idea is I have something like an AES computations, some sort of cryptographic thing here. And on the top, here go secrets, data, keys, stuff like that. Data on the top, key on the bottom, actually. And I have a setup like the one on the top right, where I can look at the circuit and I can try and determine exactly what sort of power usage is on the circuit, and not just sort of globally, but I can do that very locally. I can watch the sort of individual wires. And I'll get back to sort of this security model a couple of times in the talk. This is important. So first assumption of what an attacker is going to do is the attacker can pick a wire on your circuit, and the attacker will just always know whether there is a 0 or a 1 on the wire. Is this how it really works? No, it's not how it really works, but it's good enough for us today. And then, so now I want to go down a little bit of mathematics right away. So the question is going to be, if I look at the wire, I know what's going on in the wire, can I conclude something about secrets that have been used? What we're going to be using is statistical dependence. So here you see some more or less random Boolean function. There's 3 inputs, x1, x2, and m, and a truth table. And now you can say, well, suppose I can measure the output of this function. And suppose I want to know something about x1 or about x2. Now, if you look at x1, so x1 is false in the top half of the table, it's true in the bottom half. And then you can count the numbers of f's and t's, and they're the same in the top half and the bottom half. What does that mean? So it means that if x1, sorry, we're looking at x1, yeah. So if x2 and n are chosen randomly, and you can look at y, then you will see trues half the time and falses half the time, independent of what your value of x1 was. So that means that y is statistically independent of x1. And that's nice, right? So that means from this function, I cannot conclude anything about x1. I can measure something there. So what about x2? So okay, maybe one more remark. So note, so I'm sort of assuming that when I'm asking about x1, that x2 and m are uniformly distributed, or at least are not under the attacker's control. Let's look at x2. There we go. So the cases in which x2 is false at marked red, the other two at marked green. Now if you count the numbers of false and truths again, you see that there's a difference. So now, again, if x1 and m are random, and I measure the value of y, and I see a false, then it's more likely that I'm in the red area than that I'm in the green area. If I measure a false, I would tend to think that x1 is probably also false. If I measure the output to be true, then x2 is probably also true. So from the output of the Boolean function, I can conclude something with some probability about the input. And if I can do this lots of times, which is standard setup in the Python text, I can determine the input with arbitrary precision. And this is such. Okay. So feel free to sort of interrupt and ask questions at any time. Right? I have material for 2 hours or for 20 minutes. Okay. So this is my initial security model. The attacker can measure values d wires and do this repeatedly. And just to keep talk simpler, number d is going to be 1 in the entire time. So these are bad guy here. So I can deal with 1 dragon, I cannot deal with 2. And this is just a model. So first of all, in real life, you cannot measure the value of the wire. You put a probe and you will get some signal, and there will be some correlation with the value of the wire, but there will be lots of noise. Okay, so the attacker may be a little bit weaker than. On the other hand, if you're going to do measurements on the device, you're going to sort of measure the mix of multiple wires. And this may make your attack stronger or weaker. So this is not really my domain. This security model is relatively well accepted in the security field, and I will just. So I guess the kind of important point is, if you want to get from security to formal methods, you need models, right? So what makes the security people really proud is when they think of something that is outside of currents. So you fix your power side channels, and then they'll start looking at the noise that something emanates, or they'll figure out that your phone has a sensor that measures acceleration, and if you type your PIN code, you wobble your phone, you make conclusions about your PIN code, etc. That's stuff that makes them happy. That makes me really unhappy, right? There's no way to prove anything about a general security property. I cannot prove that the system is correct. What I can do is I can say that inside of this model, the system is correct, or whatever. Okay. So this is my introduction of the dragon. And of course, this is not new, and there is a infrastructure in place that protects your secrets. And this infrastructure is mask. So the next couple of minutes, I'm going to tell you about the security concept of mask. How's that work? Well, the secret, if you just put your secret into a circuit and somebody can measure a wire, they can measure at least 1 bit of your secret, right? This is not going to work. We're going to add randomness technology, and at the same time, we want to be able to reconstruct the secret in the end, right? I'm going to have my secrets in the original circuit in black, and then I'm going to split them in a red part and a blue part. For instance, I set the reds to a random value and the blue to the XOR of the random and my original secret. So I have 2 things that need to hold. Namely that if you know two masked values, S0 and S1, you can get back to your original value, because otherwise your circuit is useless. The other thing is that neither of these values can correlate with S, right? So the question is, how do you do that? One share is not enough to get to S, two is enough. So this is our standard setup. So start with my secret S, and then numbering is up here. So S0 is the XOR of the secret and a random mask, uniformly distributed number, 0 or 1. And S1 here is just, and S1, yeah, it's just the random number. So if you, two properties I wanted. One, if you combine them, if you XOR these two, S1 and 0, then you get S back. And the other one is that obviously neither of these correlates to S. So here S is not even in there. Here, if you XOR something with a random, then you get randomness. Okay. So this is order 1 resistance. So if you look at the right side, you look at one of the two shares, get nothing. If you look at both, you have the stickers back. You can just blow this idea up to any order, add shares, and okay. Then you want to do computations, right? And the idea is that in these computations, and I'm going to have multiple secrets, X, Y, and I am going to want the shares apart. So if you combine X0 and X1, you get the secret back. So you don't want to do that. If you but if you compare, so you can sort of combine these shares into different worlds. Red stays red, blue stays blue, will be fine. But don't combine, right? So this is our one thing to remember. You cannot combine shares. As soon as you do that, you bring back correlations. So let's do that. Let's start building circuits, master circuits. This is our simplest gate I can think of. You have a secret that you want to negate. This was your original circuit. Now we want to build a masked circuit in which, well, I start with X0 and X1, which are which if you XOR them together, you get X back. And I want to say for Z0 and Z1, and the XOR of these two has to be the negation of X. So what do I do? Maybe you can tell me. Can I do computations on red and on blue so that I get the negation? See, which are not. No. So what you can do is you can just negate one of the two bits, right? Yeah, so I don't have the proof of that. The proof of that is simple. You draw a truth table and you figure out that things work. And what you do to figure out if you do that is that you take the XOR, not X0 and X1. This is the negation of the XOR. So the masked values here are the negation of the masked values. This is okay? Questions? Yeah. So this is negation. This is my simplest case. I need to be able to do an XOR as well. If you want to compute an XOR in a masked domain, you look at each of the two domains separately. XOR X0 and Y0, which gives you first half of your result. If you do the same with X1 and Y1, the second half. Want to prove this? A matter of commutativity of the XOR, or you just draw a truth table. See if it's true. And then again, the two things that I need to prove, right, is well, so that's what I argued. You could do a truth table. So the here C0 and Z1 get the math version Z, and the other part that I want is that Z0 doesn't correlate with X or Y, same for Z1, and that's easy to see because I never come X0 and X1 don't even come close to each other, right? And the same with Y0 and Y1. I just keep them separate. Now comes the and conjunction. And this you're not going to see. This is worth the paper. This is how you compute the conjunction. And then again, you draw a truth table, you figure out if this works. So that it computes the correct value. And then you want to argue about sort of independence. Let's do this mathematically. But let me try and walk you through that. Because this is not obvious, right? So what I said that the golden rule is you cannot combine shares. And what do I do here? I have Y1 and Y0, and they're in the same formula. So this looks dangerous. You bring those two values together, you stand to create a new value that correlates. Why is it correct, nevertheless? Well, because of the order of things. So what I do is first I combine X0 and Y0. You just have to believe that this assumption is correct, right? The next thing I do is I add some fresh randomness to this. And when I do that, value of this here is uniformly random. So it doesn't correlate with any secrets. And only then do I add X0 and Y1. So this is going to be a mess, right? And you just have to believe me because I don't know willing to go. But this is subtle, right? Because let's say we do things a little bit differently. So what I have up here is I just assumed that the XOR is left associative, and that you compute this XOR before you do that one. If you turn that around, then here you combine Y0 and Y1 before you add new randomness, and this gives away your secret, right? This is subtle. I didn't see this, or you didn't see this. And this is also something that a logic synthesis tool doesn't see. Should you give this for the correct formula on top to a logic synthesis tool, they may well rewrite it to what you have on the bottom. It's functionally equivalent, and you're not going to know. So the correctness argument, security argument become subtle. Okay. I want to make things a little bit more complicated before I go into it. So the security model that I had said the attacker can look at the value on a wire. And a little bit earlier I said, well, this is sort of a power model. This is supposed to model the power usage that an attacker could actually. And if you know how chips are built, then you might know that this is not really released. If you look at the modern chips, their power usage is sort of related to values in a wire, but it's much more related to doubling. If you switch the value on the wire, this costs power. If you keep the value the same, this doesn't cost any power. Approximately, right? And this has to do with short circuits and capacitive loads. But this gives us a new security model, which is more realistic. Namely, the attacker can measure two things: one, the value of the wire, and two, any transitions. And that causes new attacks, right? Here's one. So this is more now in it's more like a software notation. But if I have a wire in a circuit that is first assigned X0, and then I assign x1, then the power usage that I have depends on whether x0 and x1 are the same. If they're the same, power usage is 0. If they're different, the power usage is 1, because precisely the XOR of x0 and x1, which is precisely what we didn't want. So, apart from the golden rule of masking that you cannot combine shares, I now have a golden corollary, which is you cannot combine shares in sort of consecutive clock cycles. That's time. And I have a little bit of subtle notation here, which I'd like you to note is the old domain that I had in R. I denoted with a box, right? So R used to be red, and now it becomes blue. I see red and blue at the same time. Now, I don't know if there are hardware experts here, but somebody is, if there are, somebody is bound to start talking about glitching. So just to prevent that question, yes, glitching as well. This gives you even more problems. I don't want to. Okay, so we have our Dorian distress, we have our defenses, but now we want to know if our hold, right? Do we need a knight in shining armor? Do we not? The castle is supposed to, fort is supposed to hold. What we need is an engineer to check that the castle is strong enough. Yeah. And so I want to give you a bit of an overview of how the verification technique works. To do that, talk about software. But I also want to, I want to talk about hardware first. But what I'm really interested in is software. So second part of this, we'll talk about software and how that works. A little bit of theory so that you know sort of what we use in the background. There are this thing called a Fourier transform of Boolean functions. These are weird things because if you want to write things easily, then you identify false with 1 and true with -1. This confuses everybody. But if you do that, you can take Boolean functions apart in sort of an XOR normal form. And this is really nice because you have that. You can read off correlations. And you can read off correlations using these Fourier functions. But let me try and show you how that works. So in this Fourier world, the simplest function that you have is an XOR. I have the truth table here with the weird ones, -1s. And you see that if you look at these things as integers, you want to get the last column, you have to multiply first two columns, right? So an XOR in this 1 - 1 domain is just a multiplication. And so this is our base. So let's look at a more complicated operation, the AND. And the AND looks simple in our normal language, but it gets the weird Fourier expansion here. But there's all kinds of interesting things here. So you look at the truth table at the end, and you look at the values here. What is the average value at the end? So 1, 2, 3, -1 is 2, 2/4 is 1/2. And this is what you see here. So if it's this 1/2. And the idea is that if you pick X and Y randomly, then on average X and Y are 0, right? Between 1 and -1. So these 3 terms go away, and what remains is the 1/2. And that's the bias of the function, right? What does it say? Well, it says that an AND is closer to false than to true. And this, I think, is something that's intuitively we all agree. Now, so this was easy because it's the bias. Now, if you want to do this for X and Y, and for the XOR of X and Y, then it becomes slightly more complicated. The coefficient that you see here should make sense. So the 1/2 here says that the conjunction of x and y, this correlates with x. X goes from false to true. The conjunction tends to go from false to true as well, but the other way. And again, we can, whether this is 1/2 or not, I don't know if that's obvious, but it should be positive. The same with y, right? The value of y and the value of x and y correlate positively. And then if you look at this precisely, there's a negative correlation with the x. So that's nice. Let's go back to the function that we started with, this one here, where I claimed that this function x and n x for x2 is statistically independent of x1 and correlates positively with x2. And I've written down the Fourier expansion here, and most of this I don't talk about. But here you see that there is no term x1, right? So the correlation between y and x1 is 0. Correlation with y and x2 is positive. That's precisely what we sort of went through. And this you can make rigorous. And there is a theorem that says that f is statistically dependent on an input s if and only if the Fourier coefficient is 0. Basically. And this is nice, right? So because now you can go through all of your secrets and you can ask, function that I have, does it correlate with my secret? Yes or no? If no, you're happy. If yes, you have a problem, right? You're both. Okay. Now, this is the theory. Now you have to put this into a tool. If you are going to compute the Fourier coefficient of all the functions in the circuit, then no surprise to you. This is not going to be more efficient than writing down any function representation that you have, right? This is going to be exponentially complex. It's because we cannot get around that complexity barrier. So you have to do some abstraction. And you know, there's lots of things to say about that. But the abstraction that we're going to do is we're going to say, well, an efficient can be either is 0 or it is non-zero. Let's say these are the exact coefficients. What I'm going to do is I'm going to abstract them all to 0 or 1. And any non-zero coefficient becomes 1 here. Now, the nasty thing that is going to happen when we do that is that we're going to be imprecise. Sometimes you combine two functions and terms cancel out, right? And then and this effect we're going to miss. So what sometimes happens is that the coefficient that is zero in our approximation. And then that means that the way we do things, we might sometimes find problems that are not real. Then you can do abstraction refinement. The nice thing about sort of 0, 1 is that we can encode this as a Boolean satisfiability problem. Of course, what we do. Basically, we're going to have one variable for every input. Or actually, we're going to have one variable for every combination of inputs and every wire that says, well, the Fourier coefficient for this combination of inputs is 0 or not. And that works surprisingly well, of course.
So if this can be reduced to that, the original problem could be reduced to SMT, right?
Yes. Yes.
So is there a reason to go with this abstraction SAT? Of course, SMT solving is more difficult, but is it to the level that we want to sacrifice accuracy and go from SMT to SAT?
We haven't actually tried this. We started off with the assumption that this is never going to work, right? So this here is actually correct. So I need a variable for every set of inputs. This is an exponential number of variables anyway. we said, well, we're going to do this in a set solver. It's going to be hard enough. And then the next thing that happens is that sort of false alarms almost never come. And if they do, you can refine. So we didn't really run into a problem. But yeah, and then we actually never thought about this. So I think it's worth a try.
So in your previous slide, you were basically looking for the function, right? And set solvers are relatively good in finding interpretations of functions.
No.
Whether it works or not for this particular Fourier transform.
Yeah, fair enough. It's worth a try. Yeah. Good point. All right. So let's arbiter fish. Yeah. So this slide is supposed to say this works. You can do AES S boxes or maybe routes AES, and you can do other cryptographic protocols, verify that their implementation is correct. If the implementation is incorrect, you actually find bugs. You find bugs, subtle things as this is quite. All right. But I wanted to talk about software. Right? So, different kind of content. So, what about this? We have this, this is called the DOM version, math version of the banana. And I take the top line here. And I've written this down as software. Right? First, you compute the end of x0 and y0, and then this thing. Then you do the XOR, and then you combine the whole. And this is just a different way of writing the circuit, right? So I can just take my existing verification tool and look at this as a circuit and run it through, and we've already done that in this thing, and it will say, yes, everything perfect. This is what people have done. So there's no intermediate variable here that correlates with either X. Does it look correct? That's right. So there shouldn't be any side channels. But then you go and you run this software on something like this. You have no idea what's going on. It's not at all clear that there are no side channels. Yeah, it's nice to look at this. But this is your real life, or actually, this is the complicated, this is an Intel processor. My life is this. So this is an IBEX core. And the experiments that I'll talk about in the next couple of minutes are all run on this core. This is a tiny little thing, a two-stage pipeline, but it's a real processor, and it's being used as a security processor by Google or by others. It's quite and so let's try and run our little piece of software that computes the end on the processor like this one, or on your favorite image of a processor that you have in your head. So let's do that. Okay, now we'll talk about different problems. So there's problems with microarchitectural registers, problems with register files, and problems with computational units. These problems, to me, are surprising. People who really know about processors, they say, yeah, but to me, this is surprising. So let's do this. So this is your assembly program here, right, in your favorite assembly language. And let's see what the processor does. Right. So we start with the first instruction here: compute the end of x0 and y0. So the processor will fetch x0, store it in some intermediate register or on some wires inside of the processor, right? It'll load the second operand, different set of wires, different register. It'll compute the end into yet another, I'll just say register, right? And you may think wire, you know more about processors. And then I have to store the result into this register T. Okay, so far so good. Then I do the same thing for my second computation here, and this is where things go wrong. Exactly the same code here with different operands. And now what you see is that R2 switches from Y0 to Y1. And this you're not allowed to do. Switch from Y0 to Y1. Your power usage depends on the XOR of the two. And this leaks the XOR of Y0 and Y1. That's secret. All right, so are correct. So this is something that is not obvious at all if you look at the assembly code, and it's only obvious if you look at the microprocessor implementation. This needs to be fixed. Problem one. Problem two, even weirder, register files. Let's say I have two loads. I load from register 4, and then I load from register 7. And I also have two shares of my secret X, register 0 and one share in register 3. So this looks absolutely harmless, right? Instructions have nothing to do with my secrets. Now, how this thing is implemented, so our register bank, 60 registers, and I load something, I want the result up here. And this is implemented by a tree of multiplexers. So the multiplexer is going to decide let a value true through either top. So let's do the first instruction. That's it. And you see that indeed the value of register 4 here goes through this multiplexer and down here and then up there and out. But at the same time, you should become suspicious. In the top half, the multiplexer tree, all kinds of things happen. This red value also goes down the multiplexer chain and stops here, isn't it propagated? But mix it up to here. And that's what's going to kill us. So switch, now we load from register 7. Again, down here, everything's fine. But now here in my multiplexer tree, now I have on the wire here, the switch, red, blue. And same problem. This is not allowed. This leaks the value of X. This is weird. And again, something that as a software design, the software designer, no way you can explain this to somebody else. Problem number 3. Computational units. I'm sort of sketching over this, but the difference between hardware and design and software design, if I can try and watch that, is that if you do an if-then else software, you first check the condition and then you decide what to compute. If you're a hardware designer, you compute both the then branch and the if branch, and then you use a multiplexer and figure out what result is interesting to do. So you're computing all kinds of things that you don't need. And this is functionally fine, but security nightmares. So suppose you do something like this. You say, well, I just want to load a constant value into register T1. Well, there's a whole bunch of opcodes, and they're all encoded differently over the same bits. So there's a different opcode that says, well, compute the XOR of two registers. And what happens here in decoder logic is that even if the opcode that I have here, load a constant, doesn't need this, I'm going to fetch both registers and feed them to the ALU and compute some output value. And this may well be the XOR of the two registers that compute the secret. So all kinds of computations go on in your processor that are not necessary, but that may lead to security risks. Again, it's something that you cannot delve in software design. So the math programs that you have carefully written that you think are secure, when you run them on the processor, they tend to be insecure. This is actually well-known facts. The 3 things that I showed you, there's a couple more problems. you have to fix somehow. Some of these things you fix by telling the software designer, don't do that. This register thing that we solve, the best solution for that is, you want to touch two shares, don't do it in consecutive instructions, or you'll get into trouble. This is something that you can tell a designer or a compiler. Works. Things like the register file allocation, you can fix the hardware. So instead of helping a multiplexer tree, you can gate these registers. You can use AND gates to make sure that nothing propagates. That's not and you can do similar things for. So that we've done for this little IBEX processor. Can come up with some rules on how to write software, and then fix your processor. And then the flow that we've done here is start with a bunch of software. You run the combination of the software in the processor through your verification tool. The verification tool says you have a problem, you fix the problem, and you do it again until you find no more bugs. Which, at the end of which you have then proven your processor correct for the software that you have given it, right? Yeah, so there's a hardware version of the IBEX for route, which we built. This is, I'll try to sort of skip over the next part. So this is not quite satisfactory because I'm proving correctness of concrete software. And of course, I want to prove correctness for software in general. What you really want is a contract, right? So you want sort of, if you buy a processor now, you will get a big book with the instruction set architecture that says an addition, what exactly that means. As part of this instruction set architecture, you should also state the leakage. Then you can verify your software against this contract. So this is what we've been working on. For all of these points, you get a contract which says, well, the add instruction leaks something. And then you have an add instruction in your processor, and you have to make sure that whatever it leaks is sort of covered, simulated by the contract. Okay. So that's it. So I wanted to talk about software security in side channels and took you on a long detour into the hardware world. Where in the end we needed this to talk about processors. So I showed you how to sort of do power side channel verifier, what the right security model is. How do you do this for hardware, and how do you do it for software? Briefly talked about the sort of hardware processor, and then what I didn't really talk about is this contract language for secure processors. So that's the story. Limitations, well, security model, right? There's lots and lots and lots of other attacks. And can I run this on an Intel Core processor? Probably not. But I can run it on interesting. Okay, so that's it. Happy to take questions. Thank you.
Yes, thanks.